Hello, welcome back to your physics teacher. We're looking at section 2.2 from the Nelson textbook, and in this one we're going to focus on adding vectors in 2 dimensions, and we're going to be using components to do so as well. And the first question we're going to do is question number 2. So a motorcyclist drives 5.1 kilometers east and then turns and drives 14 kilometers north. What is her total displacement? So let's draw the first displacement, which is east. So the notation that you use for displacement is delta D. But because in this case there are 2 displacements, you might want to start the labeling from delta D1. So the first displacement is 5.1 kilometers towards east, which is to the right. And after this displacement, and then turns and drives 14 kilometers north. So the second displacement, so that's why we can call this delta D2, is 14 kilometers north. Notice how these 2 vectors are connected head to tail, because it turns out that if we were to add up these 2 vectors, delta D1 plus delta D2, we're going to get the total displacement, delta dt. Now, delta dt is the sum of the first displacement plus the second displacement, and we do vector addition by connecting them head to tail, and the resultant, which is the sum, is from the tail of the first to the head of the last, delta dt. And that's what this question is asking us to find. What is her total displacement, which is a vector quantity? But by construction, notice that if you're going east and then north, we have just constructed a right angle triangle. So what we can do to find the unknown side of this triangle, we can take advantage that we have a right angle triangle, which means we're going to be using the Pythagoras theorem, and we're going to be using trigonometry to find the unknown angle. Now the reason why we're going to use Pythagoras is so we want to find the unknown side of the triangle. And the reason why we're going to be using trig ratios because we want to find the angle, because displacement has a magnitude and direction. So let's find magnitude. So to find the magnitude, we're going to use Pythagoras, C, A, B. C squared equals to A squared plus B squared. Delta dt squared equals to delta d1 squared plus delta d2 squared. Taking the square root on both sides, this gives us that the total displacement is the square root of the first one square plus the second one square. So at this point, all we have to do is just put in the values so we can calculate it. So we get approximately the magnitude is 14.9 kilometers. So that's the magnitude. But because displacement is a vector quantity, we also have to find the direction. And to find the direction, we want to find the angle theta, and we're going to take advantage that we have a right angle triangle. So in this case, we're going to be using SOHCAHTOA. You could use any of them, but maybe it's best sorry, I'm just looking for a color to use. Red. So from the angle theta, we can label this triangle opposite, adjacent, and hypotenuse. We have all sides of the triangle, but my preference is to use the tan ratio for this. So tan theta is opposite over adjacent. So we have 14 over 5.1. Taking the tan inverse on both sides. We get the angle is approximately 70 degrees. Oh, what happened there? Now we can write our concluding statement. Our total displacement has a magnitude of 14.9 kilometers, and the direction, from the way we've drawn it, is east, rotating 70 degrees towards north. Alright, so now we have another question. A football player runs 11 meters north, 20 degrees east. He then changes direction and then runs 9 meters east. What is his total displacement? So whenever you're drawing vectors, and in this case this has a direction that's not just clearly north or east, I like to put a small coordinate system. And then let me draw my first displacement vector, which is starting north, 20 degrees east. And again, when you have more than one displacement, you want to first label it as delta D1 for your first displacement. And this time the angle was from north, rotating 20 degrees east. So that's why I'm putting the angle there. Which is why I like to put the small coordinate system, so that way you're able to label directions easily. And then you place another small coordinate system, and then you draw your second displacement vector. But our second displacement vector is just going east, so it's very easy. Meters east is our second displacement. Our first displacement was 11 meters north, 20 degrees east. And notice how the two vectors are connected head to tail. So if I want to find the total displacement, it's just the tail of the first to the head of the last. So that's my total displacement. So my total displacement is just the sum of the first plus the sum of the second. Right, which is why I've drawn it head to tail. But in this vector addition, we don't have a right angle triangle. So we can get really complicated and we could use the sine law or the cosine law, but instead we can just use components instead. Because if you think about this question a little bit more, to find the total displacement, what we can do from now on is break the sum into the sum of its components. So what do we mean by this? We're going to break down this vector along its components. So our delta dt, we're going to break it along the x component, our delta d1 along the x component, and a delta d2 along the x component. We can do the same thing for the y components. Right, so whenever you're adding vectors, another way of doing it is by adding component-wise. So what this means is that our total displacement vector has an x component and it has a y component. But the total displacement along the x is just the sum of the displacement of the first one, x component, plus the second displacement. Likewise for the y component, is the sum of the y component of the first one, because the second displacement didn't have any y component. So let me show you what I mean in this diagram a little bit more. So what we just said is our second displacement vector actually doesn't have a y component because it only points east. So there's nothing going along the y. So that's why here this part goes to 0. And the total displacement 2 along the x is actually equal to the delta d2 itself. And because it points east, and east you're going to take as a positive direction, so you could write this as 9 meters. So our unknowns at the moment is just delta d1x and delta d1y. To find those, we're going to have to break down the first displacement into its components. This lesson is really complicated. So before we were given the angle of 20 degrees, was it? Yeah, 20 degrees, but that was closest to the y-axis. In the previous video, I showed you that it is much easier to consider it closest to the x-axis. So take advantage that it's always 90-degree angle for the coordinate system. So this means that this angle should be 70 degrees. Let's label this as the y component and this as the x. Now the reason why we find the x and the y components by first changing the angle closest to the x-axis, I showed you in a previous video that if the angle is closest to the x-axis, then the x component is the cosine ratio of it, and the y component is the sine ratio of it. So refer back to my previous video where we made this conclusion. So this makes my life a lot easier because now I can write delta d1x is delta d1, and because I have the angle closest to the x-axis, it's going to be cosine of the angle 70. And my y component, because I have the angle closest to the x-axis, is going to be the sine ratio. Delta d1 was 11. Okay, so now I can just find these by using my calculator. 3.76, I think, no, it was meters. So I found the magnitude of the x and the y component, but those are vectors which have directions. So this means that when I'm plugging them back into my formulas, well, let me make this smaller. Okay. So my x component, I have the magnitude, and the direction was pointing to the right. So this means I'm going to take it as a positive number. So this will be equal to 3.76 meters. For my y component, it was pointing up. So up, I take it as a positive number, so I'm going to substitute this by 10.34. So this makes it a lot easier to do my calculations. So my delta dtx is just going to be 3.76 plus 9. Which is 12.76 meters. And my y component is going to be 10.34 meters. There, I separate a bit so it's more clear for you. But you know, after all this work, we're not actually finished because we found the components of the total displacement vector, but to find the displacement vector itself, you have to reconstruct it. So what we did is we broke it down into x and y, but then we have to build it back up to get the actual vector itself. So let me show you what I mean by that. The x component points to the right. And my y component points up. So we found these two values, but now to actually find the displacement vector, it was the hypotenuse. So what that means is that now we're going to have to use Pythagoras to find the magnitude, and then we're going to have to use the tan ratio to find the angle to give us the direction. So it's a lot of work. So let's take this to be C, this to be A and B. So to find the magnitude, it's going to be delta dt equals to square root of the x component square plus the y component square. Right, and we got that from Pythagoras, c squared equals to a squared plus b squared. So plugging this into the calculator now. We get 16.42 meters. That's for the magnitude. For the direction now, we're going to use the tan ratio. So from this angle, we can label our opposite side, our adjacent side, and hypotenuse. So we have tan theta equals to opposite over adjacent. So tan theta is just delta dty over delta dtx. Okay, so let's calculate that. Shift 10. So 39 degrees. So now we finally found our total displacement. I think this is one of the hardest lessons of this course. It's taking me a long time, right? To just do 2 questions. This is where people usually drop the course because it's too hard. 16.42 meters. That direction, we still need to think about it. If we start east, we have to rotate towards north by 39 degrees. Wow. I suggest you rewatch that. That was pretty intense. What were the steps? When you add in more than one displacement, you have your first displacement, your second displacement. A good strategy is to add component-wise. So that means that you break down your total displacement along the x component pieces, and then you break it down along the y component pieces. Break down each vector along x and y, plug it back in, find the x and y components of the total displacement, reconstruct the triangle from the x and the y component, and then to find the magnitude, use Pythagoras, and to find the direction, use the tan ratio. So all questions are going to follow the same procedure. So once you get it once, it should work out quite well for you. Just it is very easy to make a mistake, so you have to make sure you watch your steps. I might have made a mistake too, so please leave me a comment if I did so I could correct them.